Welcome back, everybody. We are moving on to infinite series in this video. So let's remind ourselves what infinite series are. This is probably things you've seen before, say in a Calc 2 course. So what I'm going to do is start with a sequence. Okay, so I have some sequence A dot. And then immediately, without hesitation, I'm going to write down an associated sequence, which we're going to denote by putting the Greek capital letter sigma in front of it, which is going to remind you of taking a sum. And this is going to be what's called the sum sequence. Okay, so the way I get this is by looking at the first term will be A1, the next term will be A1 plus A2, A1 plus A2 plus A3, etc. So you can see in each term, I'm going to add on the next term from A. Okay, and so this is called the sum sequence for A or corresponding to A. Okay. Fine. That's maybe not the way you've seen a series before, right? And that's because the way we get the series is going to be by taking the limit of the sum sequence. Okay? So if this sum sequence A converges to some number L, then we say that, okay, we're going to write this summation, but now I'm going to actually use some notation here that will remind you of what a series really looks like. We're going to write down the nth term, and we're summing up as n goes from 1 to infinity, and I'm using a little shortcut here, just saying n greater than or equal to 1, instead of n equals 1, and then putting the infinity on top. Okay, we say that this equals L. Okay, and this gadget right here, this summation, it looks like a summation, right? It doesn't really make sense. Like we can't add up an infinite number of things this way, right? It's really a limit of sums, right? Namely the limit of the sum sequence. This is what we call the series for A, or corresponding to A. Okay, and of course it could be the case that the sum sequence diverges, in which case we're just going to say that the series diverges, meaning if we ever write down this summation with the n greater than or equal to 1, yada yada, and the underlying sum sequence diverges, then we'll say that this series diverges. So if the sum sequence diverges, okay, or possibly diverges to infinity or negative infinity, then we say that the series n greater than or equal to 1, a sub n, diverges, or diverges to infinity or minus infinity. Okay. Now, I'm going to introduce a little bit of language that does not exist in the mathematical world, but I like to use it because one of the things that students traditionally have problems with is distinguishing between the underlying sequence, A, and the sum sequence, or the series. Okay, so these are different things. Okay, people will look at a series and they'll say, oh, look, maybe the a sub n is 1 over n, and I know 1 over n goes to 0, so yes, the series converges. And they'll say it converges to 0, which doesn't make any sense, right? If I write down this series and you say, well, let's see, what is this supposed to be looking at, right? Well, it's asking about the limit of the sum sequence, 1, 1 plus a half, 1 plus a half plus a third, etc. And you can see each of these terms is already at least 1. So it doesn't make any sense to say that this converges to 0. Okay, in the back of your mind, you'd be saying, wait a second, that thing doesn't even converge at all. That thing diverges. Okay, but we know that the underlying sequence, 1, 1 half, 1 third, 1 fourth, so forth, this does converge to 0. Okay, so there's a distinction we have to make. And so it's very often the case you want to talk about the sequence, right? When you're talking out loud, you just say, oh, yeah, the series for 1 over n, right? And that's all you're talking about is the sequence. But you need at the end of the day to say, but therefore the series corresponding to the sequence converges or diverges. So I'm going to introduce a little of my own terminology that maybe you can use to simplify some of your language in the middle of complicated problems. So I'm going to put this in red because you need to be, it's like a warning, okay? Maybe you don't want to use this, but I'm going to try to use it. So if the sum sequence for A, right, or the corresponding series converges, then we say that the original sequence sumverges. Okay, and the same thing here if this underlying sum sequence diverges, then we'll say that the underlying sequence disumverges. Okay, so we're going to be able to say later on, right, when we write down, we'll just say it right now, in fact, right? So if H dot is the so-called harmonic sequence, the one we drew up above, this converges to 0, and the sum sequence diverges. Okay, so this is a famous argument, goes back to Nicole Rem. Okay, so in the language that we have here, we could say H converges and disumverges. Okay, so as a sequence it converges, but as a sum it diverges. Okay. Originally, by the way, I had the sum on the outside to match, some verges, and I had like some diverges, but it just didn't roll off the tongue as well. So disumverges, that seemed to be better. Okay. So another classic example. Okay, here this was over here. This was harmonic sequence and series, or sum sequence. But here's another interesting one. So we're going to look at all of the reciprocals of powers of 2 and say we'll start from n equals 1 and go to infinity, or we can write it like this, n greater than or equal to 1. Okay, so this underlying sequence converges to 0, right? In fact, we know that if you just have 1 over n, that converges to 0, and this is a subsequence, okay? And so subsequence convergence is inherited from the entire sequence. Okay, so what if we look at the sum sequence? So the sum sequence, this looks like 1 over 2, 1 over 2 plus 1 over 4, 1 over 2 plus 1 over 4 plus 1 over 8, etc. We keep on adding additional reciprocals of powers of 2. Okay, and so this is going to end up being, if we simplify these, 1/2, 3/4, 7/8, 15/16, etc. And looking at these fractions we're getting, we might start suspecting this is converging to 1. Okay, something we could actually prove. Okay, so this is going to, as a series, we would say that the sum 1 over 2 to the n, as n goes from 1 to infinity, equals 1. Right? So instead of writing it as a limit convergence, we write it as an equality. And that causes occasionally some confusion, right? Because really this is all coming back to a sequence converging, okay? And this is just a little bit of shorthand and maybe even a little abusive notation, okay? So, but this implies that A dot sumverges. Okay, so the original sequence, we know it converges, but it also sumverges, right? So it converges, all right? But in this case, it converges to 0, and it sumverges to 1. Okay, so even if A dot converges to 0, it doesn't mean it's sumverging to 0, right? It can add, in fact, it usually will not converge to 0. All right, maybe another example here. So let's look at the sequence 1, 2, 3, 4, 5, etc. So we already know that this sequence diverges. All right, so what happens then to the sum sequence? So this would look like 1, 1 plus 2, 1 plus 2 plus 3, 1 plus 2 plus 3 plus 4, etc. So we get 1, 3, 6, 10, 15, 21, etc. So two things. Number one, these are actually interesting numbers. These are called triangular numbers. So, and if that's not obvious, think about you put down a penny, and then you try to put down pennies underneath it to make a triangle. That requires 3 pennies. Now you put down 3 more to make a triangle. That's 6 pennies, and then 4 more. That's 10 pennies. By the way, a penny is this coin. It used to be a unit of currency back when we carried actual money in our pockets. Fun fact. The other thing we notice about this sequence is it is growing. In fact, it is growing very fast, growing even faster, right, than the original sequence. So this also diverges. And so we could say B dot diverges and disumverges. Okay, so it diverges as a sequence. It also diverges as a sum. Okay, let's see. These sum sequences, they're going to have, because, or even the series, because they come from sequences, they're going to have many of the same properties of sequences. So for example, let's do a quick theorem here. So this will be I'm just going to show a couple of these and call them linearity properties of series. I'm going to say series, even though, actually we'll mostly write these down as sum sequences, trying to avoid confusion. So let's see. So we have A and B. These are going to be sequences. And we're going to assume that A converges to some K, and that B, I'm sorry, not A but self, but actually the sum sequence. So the sum sequence for B will converge to some L. Okay. And then I'm just going to take some extra information here. I'll take a little scalar C. So these are the hypotheses, and these are, once again, very important. Okay, if we don't know from the beginning that our sum sequences converge, then what we're saying next doesn't hold. So the first thing, let's say that I have now the sum sequence that corresponds to the sequence when I multiply A by this scalar C. So I take every element in A, I multiply it by this fixed number C, and now I compute the sum sequence. And first, this is actually the same thing as if I take the sum sequence for A and then multiply each term by C. Okay, so this is just distributivity. And then this is going to converge to C times K. All right, second, if I take these two sum sequences, let's do it like this. Let's take the sum sequence corresponding to adding A and B together, right? So this is that component-wise, A1 plus B1 and then A2 plus B2, etc. I take that sum and then I take the sum sequence. And this is actually going to be the same thing, assuming again that we have this convergence to begin with, right? Both of these two. This will be the same thing as if I add the two sum sequences together corresponding to A and B. And so this converges to K plus L. Okay, and all of this just comes from the algebra of limits theorem. Okay, so you go back to the algebra of limits theorem and you'll see we can apply those things almost immediately here. Okay, so that's great. This is the beauty, right, of treating series as the limit of a sum sequence. Okay. Okay. I think that's enough introduction here to series. We'll do another video where we will go through some convergence tests. All right, we'll see you next time.